Hello, Professor Sargent here with you again. I'm going to re-examine some examples that I had recorded videos for quite some time ago, where you solve exponential equations, i.e. equations with a variable in the exponent. I've stumbled across a different approach that I had never seen before, or at least I can't remember seeing. And what we're going to do is make use of some of the properties of exponents, these three. Now, real quick, that first one, that's talking about something like x squared times x cubed, adding up the exponents to give us x to the fifth. The second one, although it might at a quick glance look similar, is not saying the same thing. It's not x squared times x cubed like the previous one. It's saying take x squared, you've already raised something to a power, and you raise that result to a power. Multiplying those together, you have x to the sixth. And from number three, we've got two different versions, but they're pretty much saying similar things because of the relation between multiplication and division. So, for example, if you have x to the second over y cubed, and that's raised to the fourth power, then we could raise the numerator and the denominator to the fourth power. And then, by the way, on this particular example, I'm back to applying the second property. So x to the eighth over y to the 12th in that case. Now, actually, what we're going to wind up doing is reading these instead of left to right when we use these properties to perhaps making solving exponential equations easier. We're going to read them from right to left. I'm going to show how we can make the answers from this method look like the answers from the other methods I showed. The reason for this is twofold. One, an equity issue, different people using different calculators. Two, how much electricity is being used if we break it down so that we can make our batteries last longer, whether we have to buy new batteries or if we're dealing with rechargeable batteries, how long it takes before we have to recharge them. Okay, so applying method one to example one. First, we are going to take the natural log of both sides because the only place where the variable is in an exponent is isolated. Here's what we get when we take the natural log of both sides. And next we are going to apply the power rule for logarithms, which will allow us to bring the exponent 2x out to the front as a multiple of that logarithm. Now, whatever natural log of 5 is, it's a number. So we can move things around with a commutative property, and we can reassociate things, regroup with the commutative property, both of those for multiplication, so that our coefficient for the x is 2 times the natural log of 5. And we're going to divide both sides by that coefficient to get our answer for x. So x is equal to the natural log of 14, all over 2 times the natural log of 5. For method 3, we're going to apply the second of these exponent rules shown up here. A to the nth power, all of that raised to the nth power, would equal a to the m times nth power. This is also going to mix working with method 2, where we take the logarithm originally in the base that we are dealing with. So first off, applying that rule I was just talking about, 5 to the power of 2x is going to be rewritten as 5 squared, all of that to the x power. 5 squared is 25, so now we have a nice situation of just raising a base 25 to the power of x. And I'm going to take the logarithm in base 25, or put another way to make it go even quicker, apply the definition of logarithms. The answer to a logarithm is an exponent, The base was 25. So by a process of elimination, it must be that we're taking the log of 14 in base 25, and that equals x. Well, next we're going to apply the change of base formula. One reason for that is so that we can get the answer looking like it did previously, and perhaps to simplify computations for our calculators. We are, in the numerator, taking the logarithm of the same thing, but in the new base, and in the denominator, we're taking the logarithm in the new base of the old base. Now that 25 came from the 5 squared up above, and we could apply the power rule for logarithms to bring this out in front. 2 times natural log of 5. And then that way, that looks exactly the same as the way we saw the answer previously. This next example is very similar to the previous one, but for the sake of completeness, since I filmed this same example some time ago using method 2, I'm going to show this one as well. So in the approach that I'm most used to, again, we have the part where the variable is in an exponent that is isolated, and so I can take the natural log of both sides right away, and then apply the power rule for exponents, bring the 3x out in front, times the natural log of 3. Whatever the natural log of 3 is, that's a number, so we have 3 times x times natural log of 3. We can move around and reassociate, so that we're going to have 3 times the natural log of 3 as the coefficient for x. And we will then, after that, divide that coefficient so that we get that the solution for x is the natural log of 12 all over all of 3 times natural log of 3. All of 3 times natural log of 3 is in the denominator. In method 3, I am going to use a little bit of method 2, but also this new approach, taking that 3 to the power 3x and applying this rule right here. I'm going to rewrite that as 3 cubed to the x power. Because 3 cubed is 27, then we have 27 to the x power is 12. Taking the logarithm of both sides in base 27, or better yet, just apply the definition of logarithms. The answer to the logarithm is x, because it's in the exponent here. The base is 27, and by a process of elimination, we must be taking the logarithm of 12 in base 27. Now apply change of base, but if we want to break this down, depending on the requirements of your teacher or of an online homework system, or just possibly to save some battery life, the 27 came from 3 cubed, and then we could apply the power rule for logarithms, bring that exponent of 3 out to the front, multiplied to the natural log of 3, and then it looks exactly like the way we saw the answer with method 1. For the last example, I'm going to apply the first property of exponents that we have shown here. The 3 to the power of x plus 5, I'm going to write that as 3 to the x times 3 to the 5th. What good does that do? Well, 3 to the 5th is 243, and if you like, we could put that in front of the 3 to the x, kind of like a coefficient. Then I'm going to divide both sides by 3 to the x, so that things that are raised to the x power are together on one side. If you would rather see the things with x, since they're on one side, on the left-hand side, there it is. There's no new work there. Just like there was no new work here, just a little rearrangement of how I've written it. I've done the same thing here. Now we're also going to apply the last of these rules. It's kind of like factoring something out. It's not really, but we can write that 8 to the x over 3 to the x as 8/3 all to the x power. And now we could take the logarithm of both sides and base 8/3, or better yet, just apply the definition of logarithms. The answer to the logarithm is the exponent x. The base is 8/3. And by a process of elimination, we're taking the log of 243 in base 8/3. Applying the change of base formula, we have this. Then the 243 came from 3 to the 5th. So I'm going to rewrite that, as well as rewriting the natural log of 8/3 using the quotient property for logarithms. And last, applying the power rule for logarithms up in the numerator, bringing that exponent of 5 out in front. And that looks like the solution that we saw in previous videos when method 1 was applied and when method 2 was applied. That's all I've got for now. Hope this helps. Stay safe and healthy.